Hi people, this is the lab 3 in week 3. So on the agenda for today is for me to show you how to do a problem where you have a mismatch in the shell thicknesses. So you basically have a model where the shell thickness is not constant, okay? Now, if you look at the book, chapter 11 of the book, this is done. However, there I'm using a solid object to extract its surface, but at the same time, I also do not join the surfaces. This is why there is a mismatch in the shell thicknesses that I have to remove by creating a connections. However, in this particular problem, I'm not going to do it like that. In this particular tutorial, I'm not going to do it like that. I will join them, but show you how to have different thicknesses when you join two surfaces. I also want local mesh refinement for shells, and then I'm going to do the problems for lab 1 and lab 2. Okay? All right. So here's the problem that we're going to do. We have a clamp like that. The dimensions are given, and over here you have a hole which is clamped, and on the top, the surface of this thing on the top, 100 on the edge of the circle on the top, 100 pounds is exerted. The thicknesses are different, as you can see, and that's the problem that I'm going to be doing. Notice that this does have a plane of symmetry, and basically you cut it along this line, along this length, and vertically down. So you have the left side and the right side, and you're going to model the problem like that. Okay, so I'm going to use planes of symmetry as you're expected to do it in on the test, and also use the most appropriate element, which in this case obviously is a shell, because it's a shell, you know, section that you're doing. All right, let's go ahead and do that, and then I'll come back and talk about the problems later on, the problems for lab 1 and lab 2 later on. Okay, so let's go ahead here and start with the part file. I think in the book I'm extracting surface, but extracting surface of a box. I'm not going to do it like that. I will do it a different way. So be my guest. If you look at other years, recordings, you might see it done differently. That's fine. So let me see now. On this vertical plane, I'm going to sketch an L. We do it like that. Inverted. Okay. Yeah, inverted L. Maybe I go here like so. Okay, let's dimension these things. I want to show you how to create the whole model and then split it on purpose. This is on purpose because you can do only half of the model, as you know. But so the dimension here is, I believe this dimension was 5. Okay, and that length was let me okay, that dimension is 10 inches. Okay, so this is 10. Okay, and exit and pad it. Let's see now, not pad it, you can't pad this. To create a surface, you have to do a extrude. So there is extrude. And I'm going to do it in both directions. So mirror extend in each direction 2.5 inches, 2.5 inches, and it goes like that. So basically what you see here is this, except that it's drawn in the, in different directions. That's all. Now, on that face, I would like to sketch a circle exactly in the middle. We'll clear it up in just a second. So that line, control this line, control the center of this. You make it symmetric. There are different ways of doing it, or equidistant point actually. This line control that line, control the center, again equidistant, okay? And the radius of this thing, I told you the radius of this thing is 1. Good. Exit. Now notice that here we have a split. Okay, right there. See, split, split. Read that carefully. It says element to cut is this face, and the, oops, let me actually, element, this is all messed up now. Cancel that because this was selected. Okay, click on the split. Read this thing carefully. Element to cut is that joint. Cutting element is that circle. There we are. Okay, and I'll do exactly on that side. Okay, so let's see now. On that face, I'm going to sketch a circle. Okay, so this control that, control the center. We'll make it equidistant, and the top, control the bottom, control that center, again equidistant. Radius is 1. Radius is 1. Exit. Once again, notice that this is selected. That's why I got that weird warning message and thing like that. Just deselect this. Just click anywhere on the screen so that this is not orange anymore. And then split that. And again, right again, this is wrong. Let me deselect this. Can I deselect it from here? Yeah, clear selection. Element to cut is that face. Cutting element is this. And we say okay. There you go. So that is what you see over here. A couple of comments that I have is there are many different ways of doing this surface. This is not the only one. The way I did it is I drew this L and extruded it. Because of that, then when I mesh, the whole thing is going to get meshed, and there are no duplicate nodes here. Because of the way I did it, there's no need to join. If you want, you can join these two pieces, but there's absolutely no reason to do that. And now I'm going to split this thing into half. So one more split. Read it carefully. Element to cut is that surface. Cutting element is that vertical plane, and it doesn't matter what side you take. I'll take the other side. How about that? Other side. It makes no difference. There we are. So this is half of that. All right, let's hide the stuff that we don't want. I don't want, you know how to hide the stuff that are sitting here? Like there are several sketches here. You can go to, I believe, tools, and then there is hide, and there is all sketches. See, that's one way of doing it. Gone. Okay. All right, so we're going to make this thing out of aluminum. Where is the material here? I keep losing my material in generative shape design. It's right there. Right there. Maybe I should take it out and put it here so I can see it. So metal, aluminum on that part, and then we say okay. All right, and now we're going to go to advanced meshing tool because I'm asked to use the advanced surface mesher. I'm asked to use the, well, I'm not asked to use it, but I'm going to do that, a surface mesher, and we'll use a finer mesh around the holes. Okay, so let's go ahead to advanced surface mesher, analysis and simulation. Actually, in this particular problem, I'm not asked to use advanced surface mesher, but I'll do it. Okay, you go there, it's a static analysis, obviously we're doing it. So there's a surface mesher. Let me change the rendering here so that you can see it better. There we are. Here is the surface measure. You click on it and you select it. Notice that I will come back. I will come back and do a refinement here later on, okay? So for example, I can put down maybe 0.3. Okay, let's put down 0.3. I say okay, and then zap it here like this. Yeah, good and okay. The only thing is that I wanted to have a finer mesh around these holes. That being the case, what I'm going to do is I'm going to uh, uh, re- uh, remove this mesh, remove the mesh, exit that, so it didn't mesh it. There is an icon. You can do that here, or you can do that in the advanced surface in the generative structure analysis. The choice is yours. Let me do it one more time here. Click on this. There's the surface. Say OK. I just erased it, but there was no reason to do that, so it looked like this. You see this icon here? You see this? This says element distribution. You click on this, and you select this edge. And how many you want? I don't know, maybe 40 elements around that edge. Same thing here. Maybe 40. I'll make this thing 20 so that you can see the difference. Okay. And then mesh it, which means that use this guy. There, you can see. Finer mesh around the hole. Finer mesh around the hole. Okay. When we are done here, we exit. And we're done. As far as the meshing is concerned, we're done. So now we're going to go to generative structure analysis. There we are. Would you like to see your mesh? Right-click mesh visualization. There we are. You see? Now this kind of thing could also have been done here, but I'll leave it like that. So deactivate this. I just realized something. There seems to be two of these. I just want one of them. Remember I did it and then deleted it and came back. Right click, make sure you delete this. Otherwise, it's going to cause a problem. All right, good. Now, there's only one surface mesh and it was refined around the holes. Okay, so let's go ahead and do the rest of the problem. As far as this edge is concerned, is clamped. We are told that this edge is clamped. These are in the planes of symmetry, so user defined this edge and that edge happen to be in the XZ plane. There is no displacement in Y. Rotation is opposite. Good. And click on user defined again. This edge and that edge also happens to be in XZ, no displacement in Y, and rotation is opposite. Actually, I could have done both of these at the same time. I did it in two different restraints, but if you had noticed that these these four pieces were all in the XZ plane, you could have done it in one shot. Okay, that's good. Now, as far as the thickness is concerned, notice that the top is 0.05, the vertical one is, this is a mistake. That should be, let's make it 0.01. Okay, 0.01. I don't want them to have the same thickness. That's the problem. Yep. All right. And one other thing, I noticed that here, the hole diameters, it looks like it says R1. I actually change that to hole diameters of 2 inches. That's okay. That's all right, no problem. Okay, let's go back here. We're going to apply a force there. Apply force on that circular path, circular arc of negative 50 pounds. And the reason it's negative 50 pounds is because the total force was 100 pounds. We're doing half of it, so negative 50 pounds. Did I do that? Let's make sure. Yep, load right here, double click, make sure it's negative 50. Yep, very good. Okay, so that's pretty much it. Oh yeah, the thickness. Look, if I run it now, I'll get this error message. You see that? It says you didn't tell me the thickness. Actually, that's what it means. Acquisition of field model failed, could not find any property checker model. That's because I did not do the 2D property. You click on it. Because of the way I did it, do you remember I drew an L and then extruded it? These are basically one piece. I didn't have to join it. Even if you had not done it, you have done it as two separate sketches and extruded, make sure you join it. Okay, so we don't have to do that here. Point one, but notice that the top one is 0.05, the side is 0.001. So this actually, I want it to be 0.05. 0.05, but this side I want it to be 0.01. So what you can do, you can put the cursor on this property right there, on this 2D property, just like you did it for beams. Right click, local 2D property. It says where? Well, this side, right? This side, I want it to be 0.01. Okay. So the way it works is that initially I put everything 0.05, and then I did the local 2D property to change the thickness here from 0.05 to 0.01. All right, now when we run it, you won't see any error messages. Yep. I look at the deflection. The deflection looks like that, or deformation looks like that. If you want numbers, how much does it deflect actually? It's going to be 1,870 inches because of the, because of the way the thickness is. 0.05 inch, so that is, let's say 1 inch is 20, I don't know, 24 millimeters. Okay, 24 millimeters. So divide that, multiply it by 5, so that's 100. Divided by 100, so that is going to be, let me see, so 0.05 inches. I have to use my calculator here. Let me see. So here, so 0.05 times, that's inches, 20 is 24.5. So we're talking about 1 millimeter thickness aluminum sheet, 1 millimeter thickness. And on it, with those dimensions, by the way, on it, I put 100 pounds. That's, a lot of deflection. So the moral of the story is that garbage in, garbage out, no problem. So the Vanessa stress and the change the or change it to average ISO. It's already average ISO, and change the rendering to material shading. Material shading right there, and there we are. Now, here's what happens. Remember, this is 5 times thicker than the side, okay? So because it's 5 times thicker, essentially this side is very flimsy, it deflects a lot. This top piece actually moves as a rigid body, pretty much, because it's so much thicker than that, 5 times thicker. So basically, this thing folds, okay, and the biggest stress is appearing here. Now, if I had changed the thicknesses, for example, if I go and change the thickness of the side from 0.1 0.01 to 0.1, you see that the position of the red line is going to go on the top, actually. Double click on this. Instead of 0.01, let's make it 0.1. So the side is a lot thicker now. And let's run it and look at the one meter stress. You see that the position will shift from that location to some other location. It appears on the top. Okay, that doesn't surprise us. Now, these things, really to trust these numbers, which I don't, because this is obviously this is going to yield for sure. You really have to do a mesh conversion study to have any trust in these things. When you get 1,000 inches of deflection, it means that there's something wrong here. Well, something wrong meaning that you're trying to do a large deformation problem in elastic range, which is not going to happen. Now, what I wanted to show you, there's one more thing I wanted to show you here, and that is, oh yeah, the type of the element. Let's check the type of the element, by the way. This is parabolic, okay? Now, obviously, if I go to linear, it's going to get a disaster. It's going to be even worse. All right, so that takes care of this problem. I showed you how to do this problem. Now notice that I did ask you to go to the advanced machine tool, because if you look at the mesh here, let me deactivate this and activate that, activate this mesh. Notice that, change the rendering here. There's no way you can get four-sided elements in generative structure analysis. If you want to get an element like that, you have to go to the advanced machine tool. Okay. All right, good. So that takes care of this problem. Now we're going to go to that problem, which is what the people in the first morning lab have to do. This is a bell spring. You're given dimensions here, you're given the thickness, and you're asked to use the most appropriate element to find the stiffness of this spring. This is a spring, essentially. You apply a load, it's going to deflect, right? So it is a spring, fancy spring. Now, to find the stiffness, all you have to do is you apply a load here and find out how much deflection you have, and you just divide the two. That's going to be the stiffness, okay? But here I'm saying use the advanced machine tool, get a fancy mesh, but only use a 40-degree setting, okay? So this is the problem for group 1 or the morning lab. Let's go ahead and do that. We'll get rid of this. We'll get rid of this. I'll start with the part file. Now, I'm not going to save anything. I suggest that you stick your saving of the parts analysis very systematically, because you're going to have to do that on the test. So on that plane, on that vertical plane, I will sketch a slanted line, which I'm going to then revolve it about the vertical axis. So here is the situation, a line like that, and I'm going to put dimensions there. So dimension from here to here, you're told is 0.75, actually 0.5, I believe. R1 is 0.5, yeah, that's R1. This should be 0.5, okay? And dimension from here to there, that's going to be 0.75. And the dimension from here to here, but the vertical dimension, right-click vertical dimension, is going to be 0.3. So what you see there, 0.3 inches, what you see there is actually the cross section of this thing. Okay, now exit, and we want to not extrude but revolve. Revolve that thing, see, revolve that sketch, right click, Z axis. I don't want to go all the way to 180 degrees, I want to go to 40. It's on purpose. Okay, let me hide this, hide that sketch. All right, now we're going to apply material to this thing. I believe that you're told that this is made out of steel, okay? So we're going to apply material. I don't have to join it, by the way, because of the way I've done it. This does not require a join, and it's going to mesh as needed. Okay? Steel, okay, and then okay. Again, did I put the steel on? Oh, maybe I didn't. Let's try it again. Apply material, steel on that part, and then say okay. Yeah, it's right there. Okay, now I made it 40 degrees on purpose because I want to use the coordinate system up here later. Okay, well, I can do that now. So I'm going to now see this edge happens to be in the vertical plane, in the y-z plane. So I have no problem with it. But the back edge, this edge in the back, is in none of these planes. So I'm going to create a local coordinate system, and this is done in tools. Remember, it's done in tools. Tools. If you don't have the tools, let me close this thing for a second. Suppose you didn't have this, you couldn't find it here. You can put the cursor on the right margin and look for tools. Because I closed it, let me see if I can find it. You scroll down until you find tools. Right there, tools. And it's going to come back. Anyway, the axis system is right here. This point, I want to put the origin there, but I want to rotate this thing about the z-axis by 40 degrees. So I'm going to say okay, more. Now I want to change these, but the way it is, I have to say okay, and then double click on it, and probably say more. Now I can rotate it. So this is going to be cosine of 40 degrees. The cosine of 40 degrees is something like that, 0.76604, 76604. And this is going to be sine of 40 degrees, 0.64278. 64278. So notice that what happens when I say, okay, this is going to rotate, right? And if you look at it from the top, you can see that this back edge happens to be in the y-z plane of this rotated coordinate system. And I'm not going to use current because I want to stick to my original global coordinate system. This is whenever I need it, I'm going to use it. Say okay. Good. So now we're going to go to advanced meshing tool because you're asked to do advanced. Go to advanced meshing tool and use the surface mesher. Click on that. It's static analysis we're doing. Here's the surface mesher right there. You click on it. You select that, and you have linear, parabolic. Now remember, this thing was 0.3. This whole height was 0.3. So let me actually make this thing 0.03. And zap it. Zap it means mesh it. There we are. You say okay. So you can see that if you don't like it, we can make it bigger, okay, or smaller elements. It doesn't really matter. And then we exit. I'm happy with this. By the way, if you want to see this mesh, right click, put the cursor here, right click, and say update all meshes. Yeah, so update me, you can see that it's already there. So we're going to, the next step is we go back to generative structure analysis. You want to see your mesh here, right click mesh visualization. You can see that, the usual stuff. Deactivate that. Now let's apply thickness. So there is the 2D property on that. And you're told that the thickness of this Belleville spring is 0.1. So let's go back here. It's 0.1. Okay, good. Now this edge is in the YZ plane of symmetry. So you click on the screen, click on the user defined. It's on the YZ plane, so no displacement, no translation in X. If it's in YZ, no translation in X. Rotations are exactly opposite, and it's that guy. Okay. This guy, this back edge, this edge, let me do actually the bottom. The bottom is resting against the ground, so it cannot move in the direction that cannot penetrate the base, okay, penetrate the ground. So no displacement in Z, it can spread out. It can move in X and Y direction if it wants to, but not through the ground. And then the back one is on the YZ plane of symmetry of not the global one, but the user one. And it says, where is the coordinate system? Is this one. And if it's in the YZ plane, no displacement in X, rotations opposite. And we say, okay. All right, we're almost done. Now, I want to find the stiffness. So what I need to do is to put a load here. On that, for example, see, on that edge, I put a load, find the deflection, and divide that load by that deflection. And I want to show you how what's going to happen here. Here's the load, distributed load, on that face, on that edge, not face, on that edge, in the direction Z. So let's say we put minus, I don't know, 100, something like that, 100 pounds. Yes, you see that? Hopefully it is in the global direction. I'm pretty sure it is. Yeah, the global direction. Good. Now, let's run it. Let's run it. Good. So look at the deflection. Deformation looks like this. Displacement looks like that. Change the color. Use the rendering like that. This is supposed to be, when you think about it, because it's a circular thing. All these bands should be circular, but on the top I have a problem. So let me show you how to fix this. You can get an estimate of the estimate of your stiffness, but you know there's something wrong. This is supposed to be nice circular, and the reason is this. So let me go out here. Let me go out here and delete that load. Delete that load. Instead of putting a load, a force on that edge, I'm going to use this guy. See that? It says load line force density. You click on it, you click that edge, it says, what is it? So let's say I put 100 inches, 100 pound LBF per inch. 100 pounds per inch. If you want, I can put 1 pound per inch. It really doesn't matter. So instead of putting a force there of 100 pounds, I'm going to put it as a line force density and run it again. You will see how the pattern of displacement will look like. Okay, right there. So let's go ahead and double click on it. Look, that's the way it should be. Now, if you want to know what is the stiffness, you need to know how much force you apply. It's very easy because it said 100 pound per inch. You know this angle, you know the radius. You can actually find that length and multiply it by, whatever force you put, 100, and then divide it by that number. You're going to get your stiffness. But let me show you a different way of doing this. Why don't we go and create a reaction sensor to find this force instead of you doing it in your head, multiply by radius, take 40-degree sector, etc. You can go and say create resultant sensor, reaction sensor. Remember that restraint which fixed this and did not let it penetrate the ground was actually, I think it was the second one, right? Right there, second one. And then you say update result, there it is. This is how much force the ground is tolerating. 34 points, 34, 30.4, 30.4, 34.9 pounds. And then you can divide it by displacement, you're going to get your stiffness. Or you do that in your head, 100 pounds per inch, find out what the length of this thing, multiply it by that length, and you're going to, believe me, you're going to come up with that number. Okay? So that takes care of this problem. All right, now I'm going to do the second problem, which is for the afternoon session. Very similar, except that we have a sphere which is internally pressurized. The dimensions, everything you're given, and you're asked to find, for example, the deformation and stress and things like that. Now, we know from our strength of material course or stress analysis course that the two principal stresses are just like this thin wall cylinder is PR over 2T. They're equal in PR over 2T. So let's go ahead and make this thing. And I'm going to take a 45-degree sector here. Okay, I'm going to take a 45-degree sector. And I can do exactly the same trick that I did here by creating a local coordinate system and rotating it. So let's go ahead, the radius of this thing, mean radius is 40 inches. So we go here, get rid of all the stuff that you don't want. I can't remember, what was the material here, by the way? This is also steel. Okay, good. So let's go ahead to part. On that vertical plane, I will sketch because of symmetry, all I need to do is to take half of this top and the bottom, and you're asked to use 45-degree sector. So I'm going to draw an arc, 40 inches radius. Good. So let's make this thing 40 inches. Okay, fit it so that you can see it. Right there. Exit. And revolve about the z-axis by 45 degrees. There we go. So what you see there is this. It looks like I've taken 90 degrees here, but I'm asking you to take 45 degrees. There it is, right there. Not 90. Good. So let's make this thing out of steel. I don't have to join, by the way, because of the way I've done it. Yeah. Material right there. Steel on that part. Say okay. Very good. And I need a local coordinate system up there, because notice that the first sketch that I did was in the X, it was in the YZ plane. No problem. But the back face is not in any of these planes. So I need a coordinate system. That's one way of doing it. It's not the only way, it's one way. Let me hide this sketch here. Okay, so local coordinate system or axis system in CATIA is in tools bar, toolbar. If you accidentally close this thing or you cannot find it, you put the cursor on the right margin, right click, and look for tools. Look for tools, because otherwise you said everything. Right there, comes back. You click on it, the origin is up there, and you say okay, but I want to rotate this thing more by 45 degrees. We did this thing in class. So that would be 0.707 cosine of 45 degrees. And this will be also called 0.707 sine of 40 degrees. At the end of the day, you have to rotate this thing because now you see that this edge is in the YZ plane. Good. And I don't want this thing to be current coordinate system. So uncheck this so that later on when you think about coordinates x, y, z, it's not with respect to this. It's with respect to the global one. Now, let me go ahead to the, because you're asked to, even if you're not asked to do it, you should be able. You're asked to, or the first group was asked to go to the advanced meshing tool and mesh this thing. Okay, so I'm going to go to the advanced meshing tool. The surface mesher. That's what they were asked to do. You should do the same thing. Here's a surface mesher. Let me change the rendering here. Surface mesher on that. Now 0.5. Remember this whole radius. This whole radius was 40 inches. So I'm going to put a maybe 2-inch size element. This 2-inch size element, and I say okay. Now let's say that on this edge, you see that on that edge, I wanted more elements on that edge. So if you look at this toolbar, before you actually do the meshing there is this toolbar here which says local specification. You click on that middle one. The middle one is this thing right there, and it says on this edge, I want maybe, let's make it 50 elements, okay? You say okay, and now you mesh it. Meshing is this icon, I call it zapping. You see what happened? So you have a finer mesh in this area. So I've shown you how to do a finer mesh if needed, okay? And I say, all right, if you need more help, please watch the video for the morning session too. We say okay, and exit, and there we are. So we have, I could have done that thing with this edge finer, that edge, but I wanted to show you how you can make it finer if you needed to. Now, we're done here, so we're going to go to analysis and simulation, generative structure analysis. You want to see your mesh, right-click mesh visualization, same thing, okay, and deactivate this, deactivate that, okay. Let's do a thickness here. Here's click on 2D property on that. What is the thickness here? I believe it was 0.1 inch. Okay, very good. So I think it's 0.1 inch. That's good. Okay, so now we're going to do the restraints. So notice that this edge happens to be in the ZY plane. So user define, see that? This edge is in the ZY plane. Therefore, ZY plane of the global coordinate system, you can see that. Don't look at this dashed one. That's the local axis that I did. So it's in the ZY plane, no translation in X, rotations opposite. Oops. Oh yeah, the coordinate system is global. Right there. Global. Say okay. This bottom edge is in the XY plane. Global. Again, user defined. However, it really doesn't matter. It's in the XY plane, that's fine. So let's do this. It does not move in the direction Z, and rotations are opposite that edge. Don't forget to do the global here. Okay. This back edge is in the YZ plane of the user coordinate system. Right there, you can see that. I rotated 45 degrees. You remember that? You click on it, uncheck all of these. So that back edge, with respect to the user coordinate system, it's in YZ plane, so no displacement in X. rotations opposite. And the, oh, did I, yeah, it says, okay, when you say user, it says which one? There's only one, but I have to go select it right there, right there. And then you say, okay. Oh yeah, the pressure. The pressure is internal, 100 psi, I believe, 100 psi. So apply pressure on that face. If the direction doesn't look right, you change it. Okay, so let's check it out. On this side, you can see, yeah, that means from inside it's pressurized. Good. And pretty much it. So let's run it and see what happens. That's okay. So it says that the meshes may not be good. Okay, let's check a few things. First of all, how does it look like? You click on the deformation and you animate it, you can see that it's just blowing like a balloon, and that's the way it should be. You pressurize it, animate it, this will blow like a balloon. You want to see one meter stress, you click on it, and you change the rendering to material shading, and you might say, oh, wait a minute, isn't this supposed to be kind of PR over 2T-ish, right? I mean, there is a little bit of thing here, but this is all the same PR over 2T essentially, right? And if you put the formula in your formula, PR over 2T, the value of P, the value of R, which is 40 inches, the value of T, which is 0.1, and work it out, it's going to be very close to this number, okay? Because uh, let me show you what happens if you plot here the principal stresses and you zoomed in. Each one of these is your PR over 2T. One is in the in the hoop direction. The other one is azimuthal direction. PR over 2T. So work it out. You should be getting the same thing. Okay. Yeah, so that's what it is. Now, the other thing is if you want the displacement, how much does this thing blow up? So you go to a displacement, double click, average ISO, and don't let it fool you. This is all almost the same number. Most of it is 0.0202, 0.0203, etc. So don't let it fool you that there are all these weird patterns here, but this is all within the point of, look at, they're all in this range, and look, they're not changing. Okay, good. So that takes care of homework number 3 for the second group, afternoon. Good luck.